Hey, this is Dr. B, and let's take a look at the shapes of lots of molecules. This is known as valence shell, electron pair, repulsion theory, or VS-EPR. It goes by certain rules. We're trying to figure out the shapes of various molecules, and we already know, at least you should know from watching previous slides, that the halogens form one bond and have three lone pairs. Hydrogen forms one bond with no lone pairs. Oxygen, two bonds and two lone pairs. Nitrogen, three bonds and one lone pair. Carbon, no lone pairs but four bonds. We can draw them like this. And from that, we can figure out the shapes of molecules like carbon dioxide. There's your four bonds, no lone pairs. There's your two bonds and two lone pairs. We call this applying honk rules. We can do this for phosgene, which is two chlorines, a carbon and an oxygen. Always draw the central atom first that has the largest number of bonds. Put your carbon in there. There's only three things around it, so something needs a double bond. That works nicely for oxygen. Well, here it is here, with its two lone pairs. Chlorine has its three lone pairs, and everything's satisfied. All of these rules here are applied. For carbon tetrachloride, which is right there, carbon has its four bonds, no lone pairs. Chlorine has its one bond and three lone pairs. The halogens and certain other atoms can form what's known as expanded octets. They can form multiple bonds, and for that, we're going to use a separate set of rules. We'll add up the total valence electrons. We'll put a central atom around it. It's usually pretty obvious which one. Notice how in all these cases there is only one, which is going to be the central atom. And then use either double bonds or more often lone pairs to make it so that the total electrons are satisfied. Notice that around that central atom you can have as few as two or as high as six bonds. They call this incomplete and expanded octets. And finally, if we need to, we can form double bonds, but only aluminum and higher can do that. In the cases we're going to see here, it's mostly going to simply be figuring out how many lone pairs are around the central atom. Watch as I do it. Okay, silicon pentafluoride anion. Total number of electrons. Silicon is 4. Halogens are 5. So 5 times 7 is 35 plus the 4 is 39 plus an extra electron makes 40. I like that because I can simply draw each bonded fluorine with its three lone pairs plus the bond. That makes 8 electrons. 8 times 5 is 40. So I see no lone pairs needed, and that would be the chemical structure for silicon pentafluoride. We just put the negative charge around there. 8, 16, 24, 32, 40. That's 40 electrons. It's a 40 electron system. Beautiful. PF5, well, phosphorus is group 5 plus the 7 times 5 is 35. We also have 40 electrons, but this time no charge, so I simply will draw the 5 bonds. For now, I don't think you really need to worry about the wedges and the hatches. That's PF5. SF4, well, S is group 6. 6 plus 28, right? That's 4 times 7 is 32. That's also a perfect match. 8, 16, 24, 32. No lone pairs needed. I made a mistake. 6 plus 28 is 34, right? So check me on that. 6 plus 28 is 34. 8, 16, 24, 32. We're too short, so we always add a lone pair to the central atom, and that's SF4. Let's see if I get CLF3 right. Well, they're all just halogens, so that's just 7 times 4 is 28. That's not going to work out very good. 8, 16, 24, that's 4 electrons extra, so I'll put 2 lone pairs around the chlorine, and there it is. 1 lone pair, 2 lone pairs. Xenon difluoride, a noble gas that can actually be coerced to form a couple of bonds. Does it have any lone pairs? Let's find out. 8 for the xenon plus the 14 for the fluorines, that's 22. So, only 2 bonds needed. 8, 16. We have 6 electrons extra. I believe this substance will have 3 lone pairs around xenon, and there they are. Let's keep going. SiF6 with a 2 minus charge, that's 4 plus 42 is 46, plus the extra 2 makes 48. That's perfect because 8 times 6 is 48, so no lone pairs necessary. Draw a big bracket around it for your negative charge. PF6 with a negative charge, that's 5 plus 42 is 47, plus the electron makes 48. Once again, that's perfect. No need for any lone pairs. SF6, 6 plus 42 is 48. Once again, that's perfect. No need for any lone pairs. BRF5, well, that's the same thing as 6 times 7, which is 42. 5 things around it. 8 times 5 is 40. I need a lone pair. And there it is right there. And xenon tetrafluoride, see if you can figure that one out. 8 plus 28 is 36, but 4 things around it. That's 8, 16, 24, 32. 4 electrons extra. I need 2 lone pairs around xenon. Okay, what would be their shape? Now that we've drawn them, what would be their shape? Well, you can just sort of spread things out as much as you can. If you have 2 items around a central atom, that geometry has to be linear. Right, spreading them out as far as possible. And if you made one of them a lone pair and removed that thing, well, it's still going to be linear, just a 2 system, so we're not even going to consider it. And that's what it would look like linear. How far can you spread around 3 things around a central atom? And by 3 things, they call these electron-dense areas. That means they're talking about either an atom or simply a lone pair of electrons. They both occupy space, so they'll try to spread out. 3 things around the central atom. Well, the best you can do is still planar. They call this trigonal planar with 120-degree bond angles. Now, if one of them, and it looks like this, if one of them was a lone pair, it still occupies space, leading us to a bent structure. Is it shown? Let's see. There it is, bent. So that's your lone pair of electrons. Let's take 4 items around a central atom. You can go into 3 dimensions and make that thing tetrahedral. And there's what it looks like, 109.5-degree bond angles. If you replace one of them with a lone pair of electrons, well, then you're still going to have a pyramid down here with a lone pair on top. That would be known as a trigonal pyramid. If you replace 2 things with lone pairs, well, it looks bent to me. And water's an example of that, bent structure. 5 things around a central atom have the interesting structure of being known as a trigonal bipyramid with 2 different bond angles. 90 there, but not shown so well here. The other ones are a nice triangle around the central region, so 120-degree bond angles there, not the 90. I mean 180 there really looks like. If there's no lone pairs, it's shaped like that. That's shown better. Notice the 120-degree bond angles around the center there. If we replace one of them with a lone pair, always take them away from the central region, and it's still going to be bent. I believe they call this a sawhorse type shape. So there it is. You can imagine how that's a little bit like a seesaw. Take away another one from the central region, and that looks T-shaped to me. Let's see if we got that right. It is. Take away another 3 lone pairs around a central atom, and that goes to, this one's gone, so it's just now at this point linear. 6 items around a central atom can be octahedral with all 90-degree bond angles like that. Replace one of them with the lone pairs. Remember, we're always going from the central atom, and that looks to me like, you may not see it, but I see a square pyramid. There it is. If we take away a central one, what's left is that, oh, where is that? Let's see. You know, it looks like a square, what would they call that? Just that one's gone, and let's take it away from the furthest side. That one's gone. This is simply known as a square planar. Since it's a planar molecule, it's not trigonal planar, it's square planar. 4 things all around in a plane and 90-degree bond angles. Take away another, that looks T-shaped to me. And you can take away yet another, so we're talking about something with 4 lone pairs around the central atom, very rare. That looks linear. And that is valence shell electron pair repulsion theory.